Okay. Here, one message for us is there's a very small driving force for coarsening. A small driving force for coarsening. We're not talking about large driving force. Okay. Here, it probably does not surprise you that coarsening, the driving force would come from reduction of total surface energy. Okay. So I'm giving an example. For simplicity, let's assume the initial particles are all cubes. That's the simplest geometry that you can pack, dense. I'm not using sphere because sphere do not pack dense, right? Here I'm using cubes because cubes I can pack dense. Okay. Assuming all initial particles are same size the cube with edge length of 0.5 micron. Okay. And surface energy, let's assume we know the material has surface energy of 1 joule per meter square, which is typical for many ceramics, many metals on this order. Okay. And then for unit volume, let's say 1 cubic centimeter of all this cube-shaped powder, the total surface energy for all the particles. Each particle has some surface energy, right? And if our total volume of the powder is 1 cubic centimeter, like your fingertip, something like that, that size, but all of them are powders. What shape of powder? Cube. And the same size, 0.5 micron. The total surface energy can be calculated. You just add it up or time it. I'm showing something like this. Okay, of course, a square gives you the area for one side of your small cube. And your small cube has 6 sides, right? So this 6a square gives you the total surface area for one cube-shaped particle. Make sense? And then times gamma, that gives you the total surface energy for one particle, cube-shaped particle. And then this term, remember, 1 centimeter is 0.01 meter. And A, let's say that's your length, 0.5. So for this volume to the power of 3, that gives me 1 cubic centimeter. How many of that small particles do I have? Make sense? This is 1 centimeter or 0.01 meter divided by edge length gives me how many along one direction, and I cube it, times the surface energy for one cube. And of course, I have A here to the power of 3. I have A squared, so cancel out. I would have A in the denominator, right? And then 0.01 to the power of 3, that's 1 times 10 to the minus 6 meter to the power of 3. This is the first term. And 6 we keep, right? A squared got cancelled with the denominator. I have A here left. 0.5 times 10 to the power of negative 6 times gamma I3, 1 joule per meter square. And if you follow the math, it comes up to be 12 joule. What does that mean? It means 1 cubic centimeter total volume of all cube-shaped particles with edge length of 0.5 micron have total surface energy of only 12 joule. Not a big number. Not a big number. Remember, when we talk about the formation energy, it's quite often on the order of kilojoule per mole. Kilojoule per mole. Here we are talking about 12 joule, very little. On the other hand, let's say if the particles have experienced coarsening, which means the particles' size are much larger, instead of 0.5 micron, they are 10 micron. But let's assume they are still cube-shaped. Make sense? So then the total surface energy for all particles, if they are instead of 0.5, they are 10 micron now. Still, the total amount is 1 centimeter cube. I'm going to use the same equation. Make sense? I'm going to put E surface area prime. I still have the same equation, except 0.5 times 10 to the minus 6 got replaced by 10 times 10 to the minus 6. Make sense? And everything else would be keep the same. And this ends up to be 0.6 joule. The total surface energy, if the particles are 10 micron, become only 0.6 joule. Okay. So now let me ask you this. What's the driving force for coarsening? It becomes the difference, right, between the surface energy. The driving force for such particle pure coarsening for 1 cubic centimeter, roughly 0.1 mole. For most material, for a lot of materials, roughly 0.1 mole is only final state minus initial state, right? We're talking about you learned thermodynamics. Final state minus initial state. I have 0.6 minus 12 becomes 14.4 joule. A negative number, which means it's a so-called spontaneous process. It's happening naturally. It wants to shrink its total surface energy. And I'm talking about absolute value 11.4 joule. Not a big number compared with chemical reaction, because for chemical reaction, quite often it's on the tens or hundreds of kilojoule per mole. Here, 0.1 mole, even by 1 mole, we are talking about 0.1 kilojoule. Make sense? So driving force for coarsening is not large. But on the other hand, compare, it's even smaller driving force for densification. You think the driving force for coarsening is not large. The driving force for densification is even smaller. Here, let's say we can have pure sintering without coarsening, which means individual particle, and after full densification, they maintain the same grain size, except they have no surface area. It's everything become grain boundary. Okay, driving force came from the small difference in surface energy versus grain boundary energy. Because we said no grain growth. Whatever is 0.5 micron, it remains as 0.5 micron. But because 0.5 micron is a polycrystalline material, there's grain boundary between them. Okay, so an energy difference between surface energy and the grain boundary energy. We are talking about that. Still, let's say initially we have particles 0.5 micron, cube-shaped, right? 0.5 micron cube-shaped, and then surface energy still the same of 1 joule per meter square. Then, for the same 1 cubic centimeter of material, net powder material, the total surface energy for all particles, the same thing, 12 joule, right? The same equation, 6a squared gives you the total surface area for that cube, times gamma gives you the surface energy for that small 1 particle. And this 1 centimeter divided by a times to the power 3 gives you how many of small particles? End up with 12 joule. And then let's compare. If all the particles are sintered together, polycrystalline material without, idealized. Let's just do idealized situation without porosity, assuming no grain boundary still, which means they still remain as 0.5 micron grains. But now, the grain boundary energy, something like this. Well, let's put that number in. It may be higher, maybe lower. Okay. Total grain boundary energy I'm giving something like this. Okay, I put an approximate sign because we are only doing a estimate based on a highly idealized model, right? 1 cubic centimeter, every grain the same size, every grain the same cube shape, a highly idealized situation. And here I'm having this equation. I put a 3 here because between two particles, initially they have two sides, but when they become a grain boundary, you double count, right? So instead of 6, I have 3. Make sense? That's factor. And then 0.01 meter divided by A, that's kind of the within the dimension. How many of them? How many of them? Actually, here we also got the cancellation. 0.01 meter square, that gives you area of the side for your entire cube, big cube. I'm talking about 1 cubic centimeter, entire cube. But now, one side, two sides, each side is this much of an area, and we are talking about how many of that? Because you remember the area is the same, and you are just repeating the area. You're just repeating for how many times? For this many times. And then 3 direction, top, front, side, 3 direction instead of 6 direction. Okay, and then we plug the number in, we get a number of 6.68 joule. 6.68 joule. Here, you may think a little bit again. This is the area for one side of my cube, which whether it's grain boundary is still the same size. And then how many grain boundaries? I have this many along one direction, but then along 3 directions, I have 3. So that's how this comes to be. And as a result, the driving force for so-called pure densification, which means from individual particles separated to grains but of the same shape and size. The difference is grain boundary total minus initially surface, only 4 joule, minus 4 joule. Also an even smaller number. The concept here is to show, okay, for coarsening, we don't have a large driving force, but for pure densification, we have an even smaller driving force. That's why quite often it's very tricky to avoid coarsening. It's very tricky to avoid coarsening because quite often the driving force for coarsening is larger than driving force for densification. If you are not careful, the particle become larger and without much densification. So that's kind of the model to tell you, okay, why we are seeing this, why we are seeing the phenomenon. Okay.